Good day, everyone. I am Engineer Mark Ersi Amorin, and I'm here to present my output for the machine problem 2 in Math 221. So for the contents, first I will be discussing the basics of C programming language, to be followed by my chosen two topics under numerical differentiation and numerical integration, to be followed by the explanation of the source code, and lastly, the results. So first, let's talk about some of the advantages of using the C programming language for numerical methods. C is known for its efficiency, resulting in faster execution times. This efficiency is crucial in numerical methods where we often need to perform numerous calculations in a short time. C is also highly portable, meaning that programs written in C can be used on different operating systems with minimal modification. This cross-platform compatibility is a significant advantage when working on numerical methods that need to run on various environments. So let's discuss the steps in preparing a program for execution in C. The first step is the design phase, where you outline the algorithm and plan the structure of your program. This is particularly important in numerical methods because having a well thought out algorithm can significantly impact the accuracy and efficiency of your calculations. So once we have our algorithm, we can write the code. In numerical differentiation and integration, so this code will involve using mathematical functions and algorithms to approximate derivatives and integrals. So after writing the code, we compile it using a C compiler. So the C compiler translates the readable C code into machine code that can be executed by the computer. So finally, we execute the compiled program to obtain the results of numerical differentiation or integration. So this is where the power of C's efficiency comes into play. Now let's take a quick look at the general form of a C program. So in this simple example, we can see the inclusion of a standard library, the main function where your code resides, and the return zero statement indicating a successful execution. So the numerical differentiation and integration code would be implemented within the main function. Part 2, numerical differentiation. So let's begin by addressing the fundamental question, why do we need to approximate derivatives? So one reason is our interest in understanding how data changes over time or with varying input parameters. So derivatives provide valuable insights into these changes. Moreover, the exact computation of derivatives can be computationally intensive, especially for complex functions. So approximating derivatives allows us to obtain reasonably accurate results without the computational burden of an exact solution. So let's delve into one of the commonly used method for approximating derivatives, the centered divided difference, or CDD. So the order 2 central divided difference is a simple and truncated formula for estimating the derivative. The formula is as shown in this slide. So it provides an approximation that is accurate to the first derivative, but not higher order derivatives. For greater accuracy, we can employ the fourth order or the order for CDD. So this formula provides a more accurate approximation, especially when you need to estimate second or higher order derivatives. On the other hand, the Richardson's extrapolation is a powerful technique used to improve also the accuracy of numerical differentiation methods such as your CDD. So the Richardson's technique enhances CDD by significantly reducing error and improving the order of accuracy. So by employing two distinct step sizes, H1 and H2, wherein H1 is set at twice the value of H2, the technique systematically cancels out lower order error terms through its extrapolation formula as shown, leading to a more accurate derivative estimate. So this precise adjustment helps us to achieve high accurate derivatives, making Richardson's extrapolation a valuable tool where precise derivative calculations are needed. Part 3, numerical integration. So in this segment, we'll shift our focus to this topic. Let's start again by addressing why we need to approximate definite integrals. So one key reason is that numerical integration allows us to approximate answers for definite integrals that are challenging or impossible to solve analytically. This is a powerful tool when dealing with complex functions or situations where the closed form solution is not available. So let's explore one of the numerical integration techniques commonly known as the composite Simpson's one-third rule. This is a method used to approximate the definite integral of a function over an interval by breaking it into smaller subintervals. So this rule involves a formula that takes into account the function values at the endpoints and the midpoint of each subinterval. So the formula consists of three main parts. The width of each subinterval denoted as variable h, which is the difference between the upper and lower limits of integration divided by the number of subintervals n. The sum of the function values at the endpoints of the subinterval. So these values are multiplied by 4 for odd subintervals and multiplied by 2 for even subintervals. The sum of the function values at the midpoints of the subinterval multiplied by 2 for all subintervals. So the resulting values are then combined to approximate the definite integral. And this technique is particularly effective when you have a smooth function and you need an accurate estimate of the integral. Part 4, the program implementation in C. In this segment, we're going to put our knowledge into action and implement the concepts of differentiation and integration into a C program. So first, let's define the problem we aim to solve. So we have here a given function f of x represented as the natural logarithm of x plus the sine of 2x multiplied by the square root of x plus 1. So our first task is to approximate the first derivative of this function at two values of x equals 1 and x equals 3, using the two different central divided difference formulas, the second order or the truncated formula and the more accurate formula. So we'll do this with our step sizes h equals 0.1, 0.01, and 0.001. So next, we aim to approximate the integral of this function from x equals 1 to x equals 5 using our composite one-third Simpson's rule. To execute these tasks, we'll require specific inputs and anticipate particular outputs. For our first task, we need the step size h, the value of x, and the method to use for differentiation. And for our second task, we require the interval of integration from a to b and the number of subintervals to be used. In terms of outputs, we anticipate the following. For the first task, the value of the function at each step and the first derivative of the function up to 9 decimal places. And for the second task, the value of the function at each node and the integral of the function up to 6 decimal places. We shall now try to explore the components of the C source code provided, focusing on the key elements of the program. So the code begins by including two essential libraries, stdio.h for input and output operations, and math.h to access our mathematical functions. Next, we define a function called function that represents the previous function f of x. So this function takes x as input and returns the value of f of x by computing the ln of x plus sine 2x times square root of x plus 1. The main function is the entry point of our program where the user interacts with the code. It starts by declaring various variables to hold input and calculation results. It also initializes arrays for the first derivative, f prime, and function values, f. User input is collected to determine the chosen method for numerical computation. The program provides options for different methods. Like for instance, the code demonstrates the second order CDD for approximating the first derivative. For the second order central difference, the code block is activated if the user chooses the OH2 method. So it takes input for x and h, which are the point at which the derivative is approximated and the step size, respectively. It then computes the first derivative using the CDD formula as shown earlier. The loop with I running from 0 to 2 calculates the derivatives for 3 different h values. The results are displayed in a table showing h, f of x plus h, f of x minus h, and the second order values. The code calculates derivatives for decreasing h values to demonstrate the convergence of the approximation. So finally, it provides the approximate first derivative at x. For the order 4 CDD, it is activated if the user selects OH4. Similarly to your OH2 method, it takes the input for x and h. It also computes the first derivative using the more accurate CDD formula. A loop calculates the derivative for 3 different h values. And similarly, the results are also shown in a table showing x, f of x plus 2h, f of x plus h, f of x minus h, f of x minus 2h, and the order 4 values. Like the OH2 method, it calculates the derivatives for decreasing h values to demonstrate the convergence of the approximation. It provides the approximate first derivative at x, and then it later asks if the user wants to compute another value or choose another method. So for the numerical integration, this code block is activated if the user selects the composite Simpson's rule. It collects user input for the lower bound represented by variable a and the upper bound variable b, and the number of subintervals variable n. It calculates the increment as the difference between b and a divided by n. The code then finds the function values at each node and displays them in a table. So it calculates the integral using the formula for the Simpson's one-third rule, which involves summing the function values in an alternating manner for even and odd indices. Finally, it provides us with the value of our integral. So we'll be presenting the results obtained from our numerical approximations and then compare them to the analytical solutions. So first, let's examine the analytical solutions. We'll be calculating the exact values of the first derivative and the integral for our given function. So the first derivative of the function at x equals -1 is given to be 0.14444, and the first derivative at x equals 3 is 4.10416. The definite integral of the said function from 1 to 5 is 4.67313. So these are the analytical solutions. Now let's compare these values to our output for the C program. For the OH2 or the truncated formula, when we enter the value of x to be equal to 1 and h 0.1, we obtain an approximate first derivative of the function at 9 decimal places, 0.144444710. This is accurate, or this is similar to your analytical solution at 4 decimal places or 5 decimal places. So here are the results for the other h values. So for 0.01, this is the result. For h equals 0.001, this is also the result. And for the other x value, x equals 3, so the result is 4.104158166. So our approximation is pretty close to our analytical solution at 5 decimal places. And finally, for the results of the numerical integration, so we enter the lower bound a equals 1, the upper bound b equals 5, and we vary the subintervals. So for the first picture on your left, the n is equal to 8, and the value of the definite integral is given as follows, 4.67931. And when we increase the number of subintervals n, when n equals 10, the value of the integral is 4.675497. These are the results for n equals 12 and n equals 14. So here are my references for this machine problem, and thank you for listening.